So today we're going to talk about some trigonometric formulas. We've seen some other sort of formulas we've called identities before, like cosine squared theta plus sine squared theta is equal to 1. Today we're going to look at three different types of formulas, the sum and difference formulas, the double angle formulas, and the power reducing formulas. The good news is you don't have to memorize these for the exam, although it does really help if you have some of them memorized, and you can do this with note cards. Let's talk about the first type of formula here, which is the sum and difference formula. So the sum and difference formula is a formula for the sine or cosine if you're adding angles or subtracting angles. So for example, suppose you want to find the sine of, we usually use alpha plus beta. Is there a formula in terms of sines of alpha or sines of beta or cosines of alpha or cosines of beta to solve this? And there is, and so we'll find that in a minute. And then we're also going to do cosine of alpha plus beta. And then on the opposite side, we also will then have the sine of alpha minus beta, and then the cosine of alpha and minus beta. And so I want to talk a little bit about how I memorize these, even though I'll give these to you on a formula sheet for the final exam. I would like for you to have a way to memorize them because it does help. And so the way that I typically memorize these is there's something the same and there's something that's opposite. Right? So when I look at the sine, I think of the sine has the same sign, but something's opposite. So what that means is you're going to have a plus in the middle here. And so the sine has the same sign, but something opposite is it's going to go sine alpha and then cosine beta. And then this will be sine beta cosine alpha. So for the sine, you have the same sign, but something's opposite, which is a sine cosine. Now for the cosine, you have the opposite sign, but something is the same, and so that comes with the cosine of alpha, the cosine of beta. And then the second term is the sine of alpha and the sine of beta. Right, so again, the idea is if you want to memorize these, something is the same and something's different. For the sine, it has the same sign, but something's different, right? That's the sine cosine part. And for the cosine, something's the same and something's different. So what's different is the sign. So you put a minus here, so there's a plus, there's a minus. And then what's different, or what's the same, is the cosine. Right, so that's how I like to memorize these. And of course, for the minus part is actually very simple. So instead of plus, if you have minus here, then you get minus here. And whereas if you have minus here, you get plus here. Right, so I don't need to rewrite the formulas, it just follows the pattern. And that's how I memorize them. Of course, they'll be given to you. So here they are again. I wrote them out. We do want to talk a little bit about why these are true. So I wanted to go through a little argument, a little geometrical argument that'll kind of prove why these are true. And then we'll actually do an example using them. So if you look here, what I did, or what I copied basically, is a drawing that has angle beta here and hypotenuse 1, and it's a right triangle. Right? The adjacent side to beta is cosine of beta, and the opposite side is a sine of beta. And what we can do is we can label each of these sides. So, like for example, this side right here, right? How do we label this side? Well, what you want to notice is we can actually set up a little ratio. We can actually say, oh, the cosine of alpha, right? So here's alpha right here, is equal to the adjacent side, let's just call it x, over the hypotenuse, right? Because of this, SOHCAHTOA business we've been doing. And so then this is over the hypotenuse, and the hypotenuse is cosine of beta. So cosine of beta. And then when you solve for x, you multiply both sides by cosine of beta, and we're going to get x equal to cosine of alpha, cosine of beta, when you multiply both sides by cosine of beta. So on this side, right here, we have x. Let's erase this. And I'm going to write what it's equal to, which is the cosine of alpha and cosine of beta. And then you can guess on this side, this was cosine alpha. I bet if you set up the ratio here, you're going to get sine of alpha, cosine of beta. And so those are those two sides. And then we can start figuring out these sides here. Right, so this is this side here. And if we want to figure out this side over here, we're going to need to know some angles. All right, so let's try to figure out some angles here. So I want to figure out what this angle is. So to figure out this angle, I know this is 90. I need to figure out this angle. Okay, so to figure out this angle, I have this blue triangle here. Oh, this must be 90 minus alpha. All right, 90 minus alpha, because this is 90 degrees, and alpha plus this angle has to add up to 90 degrees, because remember that the sum of all the angles in a triangle is 180. Right, so when you add up alpha and 90 minus 80, 90 minus alpha and alpha, you should get 180. And then over here, this actually must be the angle alpha, because you have 90 minus alpha plus 90. It's 180 minus alpha. So what do you add to it to get 180? Because this is a straight angle. It's just alpha. Oh, and this angle must be 90 minus alpha. Oh, and then this angle here, I can figure this one out because that's beta, and that's a right angle, so that's 90 minus beta. Oh, what's nice about this then, if you add all these together, you get 90 plus 90, which is 180, plus, or minus alpha plus beta, so this must be an alpha plus beta here. And then this angle here, of course, you can see is 90 minus alpha plus beta. All right, so let's try to figure out this side, and you can do the same thing we did over here. You notice this side was cosine alpha, cosine beta, so this side will be cosine alpha, sine beta. And this side over here, let's do this one in a different color. Let's use blue. So this side right here will be, instead of cosine alpha, you have sine of alpha, sine of beta, and just following this sort of pattern. All right, so remember this side we found was cosine alpha, cosine beta, and so this will probably be cosine alpha, sine beta, because the hypotenuse is sine beta, and so on. Let's make that a little bit better. All right, and then we come over here, and then what do we get? All right, so this side right here will be what? Let's change colors again. Let's go to a purple. All right, so now notice I'll use this angle right here, this alpha plus beta, because again, I'm trying to actually show why these statements might be true. And so what I can do is I can take this side, which is a 1, and this will be the 1 times cosine of alpha plus beta in parentheses. And this side over here will be the sine, 1 times the sine of alpha plus beta. All right, again, you can find all of these because if you take the cosine of alpha over beta, it'll be this side, the adjacent side, over 1. Right? So x over 1, so x is this. So you can set up these little ratios like we did over here and continuously solve for the various sides. But what you get is kind of nice if you think about it. If you want to find the sine, let's draw a line here. If you want to find the sine of alpha plus beta, well, this purple length is the sine of alpha plus beta. All right, so the sine of alpha plus beta. Well, notice this side and this side are exactly the same. And so what is it going to equal? It's going to equal the sine of alpha plus times cosine of beta. And then plus, right, so the red part plus the green part. So plus cosine alpha sine beta. Or if you, all right, so plus cosine alpha sine beta. Right, so that's where that first formula comes from. And then where does the formula for cosine alpha plus beta come from? Well, here in purple, you can see right here, that purple side, that's the cosine of alpha plus beta. So you see it's cosine of alpha plus beta. And you'll notice this, it's this opposite red side right here, cosine alpha times cosine beta. So cosine alpha, cosine beta. That's supposed to be an alpha there. And then you take off the blue side, right? So if you take this red side and take off the blue side, you get this purple side right here back. And so we'll take off, so minus sine of alpha, sine of beta. And you notice that's where this formula comes from right here. Right, so I just wanted to give you guys a way to sort of visualize this. You don't have to memorize this or anything. I just hate to give you guys a formula without an explanations. And there are some easier ways to remember this, but we have to have some experience working with complex numbers, which maybe if I have time I'll talk about in class. But let's do a problem with this, because the problems are actually a lot easier. So the idea is you want to use the sum and difference formulas to find the exact value of the expression. So we want to find the cosine of 75 degrees. Now remember, on your calculator you can always do this. If you have your calculator, you can take it out and you can always find it. So hit mode, because you want to be in degrees right now, so I'm in radians, so now I'm in degrees. And then you just hit the cosine of 75, and I'll tell you exactly the answer. So that's the answer I want, 0.2588190451, blah, blah, blah. All right, to find that answer, though, exactly, okay, not a decimal approximation, which what your calculator gives you, what we can do is we can use one of these formulas. So look at these formulas up here, and you're going to use, either this one or that one. My guess is you're probably going to use this one here, cosine of one angle plus another angle. So if you think about 75 degrees, and remember, you only know certain angles, right? You know 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And we know the cosine of those angles, right? Cosine of theta, you just have to remember the cosine of 0 is equal to 1, so it's like root 4, root 3, root 2, root 1, root 0, all divided by 2's. So divided by 2, divided by 2, divided by 2, divided by 2, and divided by 2. So this is what I know, the cosine of these angles. And so the idea is, can you make a 75 out of 0, 30, 45, 60, or a 90? And of course you can. The first one, the most obvious one to me, is just 30 and then 45. So here, what we'll write is that this is the cosine of 30 degrees plus 45 degrees. And then we can use the formula here. Now again, you can just copy it down. You can remember the little saying, something is the same and something's different. So for the sine, has the same sign. So this has opposite sign, so it's going to be a minus here. And then something has to be the same, so that means it's going to go cosine of 30 degrees, cosine of 45 degrees. And then over here you're going to have sine of 30 degrees, and then sine of 45 degrees. And now it's simply a plug and chug, so you have to look and say, okay, for the sine of 30 degrees, what do we have? We have root 3 over 2. So this is root 3 over 2. So I plug that in for cosine of 30, times cosine of 45 is root 2 over 2. It's right here. Minus, oh, I also need the sine. Okay, so right up here maybe, I should have done this one too, because I'm going to need it. Sine of theta goes the opposite way, right? So it's root 0 over 2. Root 1 over 2, root 2 over 2, root 3 over 2, and root 4 over 2. All right, so for the sine of 30 degrees, let's do that in a different color. So let's do it in green. So where's 30 degrees? Here it is. So that's root 2 over 2, which is 1/2, times sine of 45 degrees is root 2 over 2. And then we can do this computation. So root 3 times root 2 is actually a root 6. So square root of 6 minus, and then 1 times root 2 is just root 2. And that's all divided by 2 times 2 is 4. They have the same denominator, so 4 and 4. So we get root 6 minus root 2 all divided by 4. And that should be our answer. Let's check it on our calculator to see if we did it right, because we know what the answer is. We already computed it. And so what we can do is then take the second square root of 6, and then take away the square root of 2, and then divide all that, kick it out, divide all that, in parentheses, divided by 4. And you see you get exactly the same answer, so that's the exact answer, right, value for this expression cosine of 75 degrees. So that's one way you can use these formulas. Probably the most important thing is that you're just aware that these formulas actually exist because they're used to prove various formulas in calculus. We need them to prove certain things. So as long as you're aware that they exist, it's nice to have them memorized because then you can recall them relatively easily if you ever need them. Let's move on to the next type of formulas. These are called the double angle formulas. Right, the reason they're called the double angle formulas, if you notice, they work with double the angle. So sine of 2 theta versus cosine of 2 theta actually can also be written in terms of sines and cosines. We should understand a little bit why, and it's actually very simple if you think about it. So why can you write sine of 2 theta as 2 sine theta cosine of theta? Well, remember, what's sine of 2 theta? Well, sine of 2 theta is just sine of theta plus theta, and we just learned an identity for that, right? They're up here, right? These sum and difference formulas. And so if you look at this identity, what you're going to notice is if you have alpha and beta and they're the same, right? They'll have the sine of the angle times the cosine of the same angle plus the cosine of the angle times the sine of the same angle. So look here, you'll have the sine of theta times cosine of theta plus the cosine of theta, if you want, following that formula, times the sine of theta. But these are exactly the same things. So what happens is you get out 2 times the sine of theta cosine theta. So that's where that first identity actually comes from. And of course, the second identity comes from the same spot too. If you look at the cosine of 2 theta, that's really equal to the cosine of theta plus theta, which equals, if you look at the formula, so here's the formula for the cosine of alpha plus beta, it'll be the cosine of theta times the cosine of theta, and then minus sine of theta times sine of theta, which is simply equal to cosine squared theta minus sine squared theta. All right, so these two identities, these right here, come from the basic sum and difference formulas. Now these two pieces come from the fact that also this cosine squared of theta plus the sine squared of theta is equal to 1. So that was one of the Pythagorean identities we looked at last time. And so if you take one of these identities, let's say here, let's do 2 cosine squared theta minus 1 if you want to look and see that one. If you solve this for sine squared theta, what do you get? So if you solve for sine squared theta, this will be equal to 1 minus cosine squared theta. And what we're going to do is we're going to take this, right, and plug in this for it because it's the same thing. So this will be equal to your cosine squared theta minus, and in parentheses, 1 minus cosine squared theta, which is equal to cosine squared theta minus 1 plus cosine squared theta, which equals 2 cosine squared theta, minus 1. So that's where this piece comes from. And then, of course, you have the second piece here, the second double angle formula, right, for cosine of 2 theta is 1 minus 2 sine squared theta. And where do you think that comes from? Well, that comes from right here. If instead of plugging in for sine squared, you could actually solve this for cosine squared theta, which is equal to 1 minus sine squared theta. So if you take this out and replace it with this, you'll get this second formula. Right, so all these formulas come from someplace, and it's not too hard to see where they come from if you think about it. And they all kind of build on each other. Now remember, the places where they're actually used is to simplify expressions. And so let's do an example involving these. And so here's one. So suppose the cosine of theta is equal to negative 4 over 5, and theta lies in the third quadrant. And we want to find the tan of 2 theta. All right, so let's draw a picture of this to find out where everything lives. So it says we live in the third quadrant, so my angle theta is somewhere down here. All right, so this is my theta. And then you have this cosine is equal to negative 4 over 5. Remember, this is SOHCAHTOA, so we can make a little right triangle in that quadrant. And because we're working with the cosine, we have the co, which is the adjacent side, over the hypotenuse. And so this must be the -4 right here. Always put the negative. And then this is my right triangle, and then the hypotenuse must be 5. Always put the negative with either the adjacent or the opposite side, depending on what's given. And so then you can figure out this side. We can call it b. So we can actually figure out that side. We're probably going to need it, so I might as well do it. So -4 squared plus b squared is equal to 5 squared. And so that tells me that 16 plus b squared is equal to 25. And of course, then b squared is equal to 9. And you take this plus or minus the square root, and we want the negative because you can see it's going down. And so then this is -3. And so b is equal to -3. All right, let's find the tan of 2 theta. Now you know that triangle. This shouldn't be too hard. So let's find tan of 2 theta. Now there is a double angle formula for tan of 2 theta, but I usually don't teach it to you guys because, I mean, you can look it up, but you don't really need it because if you have the double angle formulas for the sine of 2 theta and the cosine of 2 theta, you can use those, and that's where the double angle formula for tan of 2 theta comes from anyways. So I try just to teach you sort of the minimal number of formulas you really need to know, which you should be familiar with. And in fact, remember, it would be best if you memorize these by using note cards. I certainly did when I learned them. And the payoff has been tremendous, because this is something that students often overlook, but it always comes up again and again and again. Remember, trigonometric functions are some of the oldest functions that we have. They're well over 2,000 years old, so they're all over the place within our technology. And so what I can do here is I can rewrite this as sine of 2 theta divided by cosine of 2 theta. And that's equal to, then, I can use these identities, right, these formulas, sorry, these double angle formulas. I can use this one. And it doesn't matter. You have 3 to choose from here, so it really doesn't matter which one you choose. So I always just go with the first one because it's the first one there. So on top, I'll have 2 sine of theta times cosine of theta. And then on bottom, I have cosine squared theta minus sine squared theta. And so what this problem reduces down to is finding the cosine of theta, which I already know. The cosine of theta is -4/5. And then I just need to find the sine of theta. And then the sine of theta is actually pretty easy to find because I have the right triangle here. The sine of theta is equal to the opposite, which is -3. So it's this side over from the number 5. And now it's just a plug and chug. So it's 2 times the sine of theta, which was -3, divided by 5, times the cosine theta, which is -4/5, all divided by cosine squared theta. So you're going to take the cosine of theta, which is -4/5, and you're going to square it. And then you're going to take off the sine of theta, and you're going to square that. So -3/5 quantity squared. And so that's equal to, it's equal to what? Well, so -3 times -4 is +12. And then times 2 is 24. So you have 24/25. All divided by, on the bottom, you have 16/25 minus a 9/25, which is equal to, so we get 24/25, all divided by 16 minus 9. So if you go down 6, you get 10, and 3 more is 7, I think, right? Yeah, that looks good. 7/25. And then you multiply, of course, by the reciprocal. And so we have 24/25 times a 25/7. And these are going to cancel, the 25s. And so we just get 24/7. So that's our answer, 24 divided by 7. All right, so let's move on and look at the the last type of formula we're going to talk about, which is the power reducing formula. Now, I don't see this used a ton in Calc 1, but I do see it used often in Calc 2. So every Calc 2 class will use this formula. And it has something to do with called integration, when you have to integrate a square of a sine or a square of a cosine. It's a pretty easy formula actually to memorize. At least I like to memorize. I mean, it was easy for me to memorize, and it might have been because the problem that it's actually used in is so hard to solve if you don't memorize it. But here are the formulas here. And so we have this one here, cosine squared theta equals 1 plus cosine 2 theta over 2. And then you have this one here, which is the same thing, but instead of plus, you have minus. So I kind of like this symmetry. It's easy for me to remember. Now, where do they come from? Well, of course, they come from the formulas we just did before. So what we want to look at is, if you think about this, if you think about this side and this side, you can actually solve this for cosine squared theta. So let's do that. Let me show you where these actually come from. They come from the fact that we know cosine of 2 theta is equal to 2 cosine squared theta minus 1. And if you solve this for cosine squared theta, so we add 1 to both sides basically. So we'll do this nice and slow. Add 1 to both sides. See, cosine of 2 theta plus 1 is equal to 2 cosine squared theta. And then if you divide out by the 2 on both sides, you get exactly what I have written up there. So we have cosine squared theta on the right hand side equal to, and then I'll just copy this down over here, so I'll rewrite it like this: 1 plus cosine of 2 theta all divided by 2. The same thing will happen if instead of, we'll use this one here, but we choose this piece here. And so if we solve this for sine squared theta, you'll see we get this one popping out right here. So they just come from the double angle formulas. Right, and they're called the power reducing formulas because it takes powers of cosines and reduces them to just a cosine. Same thing with a sine squared. It takes a power of sine and reduces it to, again, just a cosine. So there's no more powers on the trigonometric functions that are left over. Let's take a look at an example real quick so you can see how we might use these. And so in this one, this is your old favorite, right? So verify the trigonometric identity. So remember the idea behind this. We start on the left, and then we're going to end with this right. And so we'll write this down: 4 cosine to the 4th x. And I want to show it's this right-hand side. Now you notice in this right-hand side, you don't have just the cosine of x, you have the cosine of 2x. So when I say, when I see a problem like this, I'm like, I have to somehow go from cosine x stuff to cosine 2x stuff. That means I'm probably going to use one of this type of formula, because you notice that this goes from cosine stuff to cosine 2 times the stuff. And so what you want to notice is that this is not cosine squared x, it's cosine to the 4th x, but you can rewrite it in terms of squares. This is cosine squared x times cosine squared x. And so then the idea is to replace these two things with this thing written twice. So let's do that, and then everything will just fall out probably. And so then I have 1 plus, instead of cosine 2 theta, you write cosine 2x. And let's put parentheses around the 2x just to make sure it's clear that's inside there. Then all divided by 2. And then times another cosine squared theta, so times another 1 plus cosine of 2x, all divided by 2. And so what's going to happen here is that 2 times 2 is a 4, so they're going to cancel with that 4. So this 4 is going to cancel with those 2 times 2. And I'm going to be left with this. I have 1 plus cosine of 2x times another 1 plus cosine of 2x. And so you can FOIL this out, or if you want, you can just use those arrows, right? So like 1 times 1, and then 1 times this is what? So you get a 1 plus a cosine of 2x. And then plus, you take cosine 2x times 1. So cosine of 2x. And then plus a cosine 2x times a cosine 2x is cosine squared of 2x. And so what does that equal to? That's equal to 1 plus 2 cosine of 2x plus cosine squared 2x. So that's an example. using these power reducing formulas. And again, you can see that you started with the power of cosine to the fourth, and you reduced it to a cosine and cosine squared. So you reduced the powers. So I hope you can kind of see how you might use these formulas. And basically, the idea is we can now do some of the problems we've done before, but now we'll do them with these new sorts of formulas. So the last example I want to do is involving solving an equation, and it says use an identity, right, to solve the equation on 0 to 2 pi. And so here's my equation, sine of x times cosine of x equals square root 3 over 4. And I have to use an identity, or a formula, I guess. They probably should say formula here. But it's easy to see which one you're going to use. You come over here and you say, okay, well, do you see a formula involving just the sine of an angle and the cosine of an angle? And I'd say, you can go through these and just put x's on them, like a no, and a no, and a no, no, no. And then, oh, yeah, right here. I see there I have a sine of an angle and a cosine of an angle. The only problem is I have a 2 here, and I don't have a 2 there. But you can take care of that if you want. So one way to take care of that would just to be multiply this whole thing by the number 2. So if you write 2 times sine of x, cosine of x, and then you multiply this side by 2, then some of the 4 stuff cancels. So what you get is root 3 over 2. Right, so you multiply that by 2, you get 2 over 4, which is 1/2 basically. Now what I can do is I can use this formula right here, but instead of a theta, of course, you're going to write an x. You just write x here and an x here and an x here. So I'll get sine of 2x is equal to root 3 over 2. And now I can solve this equation for x between 0 and 2 pi. The first thing I want to do is find out where the angle 2x actually lives. So I have all students take calculus. And this tells me where the angle is going to live because I see here I have a positive number. So I know the angle has to live here, or it could live here, but it can't live down here in these 2 quadrants because the sine of angles in those 2 quadrants are negative. So I'll just draw the angle. I need to find the reference angle. Right, so remember, to find the reference angle, I need to use the reference table. And so for the reference table, let's just draw it again. So I have 0, and let's use radians this time. So pi over 6, pi over 4, pi over 3, and pi over 2. So every time I need to use this reference table, I just make it. It's not terribly difficult to make, and it helps me remember it. And the more often you make it, the easier it is to recall the exact values. And so remember, you have to remember the sine of 0 is 0, so go square root 0, square root 1, square root 2, square root 3, square root 4, and these are all divided by 2's. 2 and 2. And so I'm looking for when it's root 3 over 2, so right here it's root 3 over 2. Oh, and that's pi over 3. So that means my reference angles here are pi over 3. And then I can read the angles off, like telling time. I start here, and I go up, and that's just a pi over 3. So my first answer would be 2x equals pi over 3. And then remember, you can add any multiple of 2 pi. So 2 pi n, where n is a nice number. It's the numbers that you count up or count down in integral amounts, like 1, 2, 3, 4, 0, negative 1, negative 2, negative 3, negative 4. So n's an integer. And then there's another answer. All right, where's the other answer at? The other answer, it starts here too, but it goes all the way around to right here. And so to find that answer, you can just take pi, like you go halfway around, and go back pi over 3. And so remember what that is. That's really 3 pi over 3 there. Take away pi over 3, which is 2 pi over 3. And so my second answer would be 2x plus, I'm sorry, this is a pi over 3. Let's make sure that's right. That's a pi over 3 there, not pi over 2. And so this is 2x, and it's not plus, but it's equal to, and that's a 2 pi over 3. And again, you can add any multiple of 2 pi n. And it's really important you add this 2 pi n, where n is an integer, because you don't just have the angle equal to it, just x, it'd have 2x in this sense. So you have to get rid of that 2. So let's get rid of that 2. And again, it's pretty easy to get rid of if you think about it right. So to get rid of the 2 over here, what we're going to do is we're going to multiply this whole thing by 1/2. Or divide by 2, however you want to look at it. So then you get x equal to pi over 6, because that's 2 times 3, plus here the 2's are going to cancel because you're taking 2 and dividing by 2. And so you get pi n. N is an integer. Do the same thing here. We're going to multiply by 1/2. And so I'm going to get x equal to, and this one will be 2 pi over 6 plus pi n. N is an integer. And I guess as 2 pi over 6, we can actually reduce that, can't we? So maybe you can just see if you multiply the bottom by 2, the 2's cancel. And so here you're just going to get pi over 3. And then you want to count them off, because you only want the ones between 0 and 2 pi. So if n is 0, you're just going to get pi over 6, because this term's going to go away right here. So you just get pi over 6 here. Then if n is 1, you're going to add pi to it. So pi plus pi over 6 is 7 pi over 6. So those are the two answers there. If n is 2, then you have 2 pi plus pi over 6, which again is too big. It'll be outside 2 pi. If you start with 2 pi and add something to it, that's positive. It's bigger than 2 pi. Whereas over here, we'll start again with n being equal to 0, so we get x equal to pi over 3. And then when n is 1, you're adding pi to pi over 3, so it's adding 3 pi to pi basically, so you get 4 pi over 3. And then when n is 2, it's too big. 2 pi plus something is too big. Also, when n is negative, it's too small. And so those are our 4 possible answers. Now, you can also check these answers pretty easily on your calculator by taking this original equation here and plugging in the answers you found. So let's just pick one just so you can see how you might check this. So you can take like the sine, and let's do 7 pi over 6. So 7 second pi over 6 in parentheses, and then cosine of 7 pi over 6. And then before I hit enter, I better make sure I'm in radians, otherwise these answers will be wrong. And notice I'm in degrees, so if I hit enter, I actually won't get the right answer. So I'll hit enter on radians, hit second quit here, and now hit enter, and this should be square root 3 over 4. Now let's check it, see if it is. So square root 3, kick it out, divide by 4, and I see that, yep, I did it right. And so you can check all those answers that way to ensure that you got the correct answer. So those are the 3 formulas you need to be familiar with, right? The sum and difference formula, double angle formulas, and the power reducing formulas. Again, you don't have to memorize them because I will give them to you on a formula sheet, but it is really nice if you do have them memorized, and it's not hard to memorize them if you use note cards, and I think it'll really help you guys.